recording for titration. So titration is a methodology that you can find concentration of unknown solution if you have a standard. Endpoint of reaction as a review is where the color change takes place. When you start with, let's say, acid, you have your indicator of phenolphthalein, which you know what the color change is, what color change is expected from your indicator, and what's the approximate pH. So you choose proper indicator, and your proper indicator is going to show color change at the time of the coolants. That means when the number of moles of acid equals number of moles of base. So equivalence point is a point that reaction is complete. That means number of moles of acid equals number of moles of base. End point of reaction is when the color change takes place. And what is indicator is organic compound, is a weak organic acid or organic base that has different color in acidic solution than the basic solution. So at the point of equivalence point is going to change color. If you start with a strong acid and you add a strong base, what is going to, how the graph or how the pH is going to change? Of course, you started with the strong acid. So with the strong acid, you start with very low pH. And as you are adding base, some of the acid is going to be neutralized. It changes to salt and water. That's the product of the acid-base titration. A strong acid, a strong base is going to give you neutral solution of water and salt. Then, as a result, number of moles of the acid is going to decrease. And since the number of moles of acid is decreasing, the pH is going to increase slowly. When you see this big jump, this is very close, it's happening at the time of the equivalence point. So when all of the acid is consumed and you have just a couple drops of the base extra in the solution, right away your solution is going to change direction from acidic solution to basic solution. And that's where you see that big jump. If you have a strong acid, a strong base, the jump is like a big jump here at the equivalence point, and then it changes from the acidic solution to a basic solution. This is just addition of just a couple drops, really. The volume that has been used for the equivalence, to reach the equivalence, this is the volume that is used for calculation. So if this value, let's say if it's 25, then 12.5 is going to be V1/2. This is the half the equilibrium. So half the equilibrium or volume at halfway to the equilibrium. So at 12.5, you have half the equilibrium. So this pH for the weak acid is like a pKa, but I just want to make sure that this is the volume that is used for the calculation, and half of that is the half the volume at the equivalence point, to the equivalence point. If you have a weak acid and a strong base, for the weak acid, instead of starting with the 1 that we had with the strong acid, now we are starting with a higher pH because you have a weak acid. That's one of the differences. The other difference is, you see that the change in the pH is is not significant, is very low change in pH, because you're adding a strong base to a strong acid. You still have some leftover of the strong acid, so it keeps the pH very low. But when you have a weak acid, the increase in pH is going to be more significant because you're adding a strong base. So if you're adding a strong base, increase in pH is going to be more significant. The starting pH also is going to be higher because you started with a weak acid. So these are some of the changes. The second part, the jump is not as huge as when you had like a strong acid, strong base. The second part, because after the equivalence, you still keep adding a strong base. It is very similar to the previous graph where you had a strong acid with a strong base. So I'm going back and forth so you can compare the two graphs. Okay? You see the second part? It's very similar. This is the second part for a strong acid, a strong base. This is the weak acid, a strong base. After the equilibrium, you end up with a strong base, and it's very similar to the previous graph. So you see that I pointed few differences. You start with the higher pH, still is in the acidic range, but instead of 1, you started with the 3. Change in pH was more significant with the initial addition of a strong base because this is a weak acid, and the second part was just the other. So be familiar with the type of the graph that you're getting. Before you add any of the solution from the burette, you see the pH is high. So you must have start with a basic solution. So you have a weak base to begin with. So the pH is going to be higher than 7. So you start with the basic solution. Is not 14 because you don't have a strong base. Is a weak base. And then you keep adding acid. And as you're adding acid, you see the change in pH is significant. It goes from 11 to 3, like 3-unit change in the pH because you're adding a strong acid. So significant effect in the pH. The pH is going to be lower. Then you are going to see the endpoint of reaction when there is a big drop or change in the pH from basic to the acidic solution. It would move, and then you have the addition of the acid in this area. So there is no more base left. After the titration, you're only adding your standard, which is the addition of the acid in this case. So the pH is going to be low, but the change is not that significant. So you are going to end up with the pH of 1 because of the strong acid that you are adding. So weak base, strong acid. That's the graph that is shown. The titration involves like the change in pH. See, change in pH. After you add 5 milliliter, pH is changing. After you add 20 milliliters, pH is changing. After you add 45 milliliter, pH is changing. When you do calculation, you're not one point like what you do in 1045. You just add enough acid until you see the color change, and then you stop. Then you look at the burette initial final volume, and then you do the calculation based on the stoichiometry and then number of milliliters and the concentration. Here, the concern is what would be the pH after addition of limited amount of the standard. So what is happening in between? So basically, you should be able to do the calculation for change in pH during the titration. So we have 100 milliliter of H NO2, which is a weak acid. We have the Ka. We know this is a weak acid, so we have the Ka value, because for a strong acid, we don't have Ka value. Concentrate, the dissociation is 100%. 0.1 molar sodium hydroxide, so is a weak acid, a strong base. What is the pH at the equivalence point? The pH at the equivalence point, that means we have added enough base to react with all of the acid that we had. So we have the acid plus base, it gives the conjugate base and water. So acid, base, solvent, and water. Initially, we are going to, when we are doing calculation and we are trying to subtract, please do not subtract concentration. We cannot subtract concentration because concentration could be the same. So if you subtract this 0.1 from 0.1, you end up with 0 for all numbers. So you cannot subtract concentration. When you are setting up ice for titration, you need to convert those to number of moles. Subtract the number of moles, you end up with the final number of moles, and then that final number of moles at the end point of the reaction, then you can convert it back to concentration before you can use your Henderson equation or the Ka or Kb before you can use equation, because your equation is going to be based on, if you have a mixture of acid and base, conjugate base, a weak acid and conjugate base, you could use the Henderson equation. So it depends on what you have on the product side. So this is going to be consumed entirely, so there would be no acid left, so you only end up with this NO2 that is going to hydrolyze. So you cannot use actually Henderson equation, so you're going to use the Kb value for this base. At the beginning, you have 0.01 mole of the HNO2. How do we find that? Again, molarity times molarity, which is 0.1, times volume in liter. So number of moles of HNO2 equals 0.1 mole per liter times 0.1 liter. And where do you get that 0.1 liter? This 100 milliliter is 0.1 liter. So this is the moles of HNO2, number of moles for HNO2. And 0.01 moles of hydroxide, because we are looking for equivalence point. At the equivalence point, this must be the same. Same number of moles of base is going to be used in order to cancel the same number of moles of the acid. At the end, the acid and base is neutralized. You end up with salt and water only. So final volume, so you have the number of moles again, but you cannot use number of moles for calculation of pH. You must change that to concentration. How do you change the concentration? Concentration is molarity equals number of moles divided by volume in liter. So number of moles we have, what's the volume? We have 100 milliliters, 100 milliliters of the base added together, because the concentration is the same, the volume is going to be the same, so we have to add 100 milliliters of this base in order to neutralize all the acid. Then we have 200 milliliters as the final volume. number of moles of this NO2 or the conjugate base or the salt divide by 0.2 liter, we have the molarity for the NO2 minus. The pH, going back to last chapter, what did we have for NO2 minus? NO2 minus is coming from weak acid and a strong base. So this salt is a basic salt, basically. If it hydrolyzes, it's going to give you hydroxide ion. So initial concentration for the base, 0 for the product, the variable x, and you are going to set up the K expression. K expression in this case is going to be for concentration of the products over concentration of the reactant. We cannot write water because it's a pure substance. For the pure substance, we don't write in the K expression. So concentration of product over concentration of the reactant. Then you solve for x. You can approximate this and solve for x. When you solve for x, x equals concentration of hydroxide ion. Then you can calculate the pOH. When you have the pOH, you subtract that from 14 to get the pH. So you find the pH of the solution at the end point of the reaction to be 8.02. So it's kind of, you learn about how to calculate the pH for weak acid, for weak base. This chapter is using those formulas and equations that you learned in previous unit in order to use it for the application. One of the applications is for titration. Another application is like for determining solubility and pH of a buffer solution, for making buffer solutions. So it's not the repeating of the same chapter. This is like a higher level. Basically, it shows the application of the knowledge that you learned in previous chapter. Okay, for those of you who are here, can you tell me if you have any questions? Any questions? Can you hear me? Do you have any questions? No questions? Okay. Okay. What are acid-base indicators? Based on definitions, I said those are either weak acid or weak organic base, that they have different color in acidic solution and different color in a basic solution. So for previous reaction, when we had the pH 8.2, calculated pH at the equivalence point as 8.2, which of these indicators would be proper? The proper indicator that shows color change at or with the narrow range in the pH of 8.2 for previous problem, based on this, is going to be either phenolphthalein. So you can use phenolphthalein because as soon as the pH changes to 8.3, it's going to change color. You can use the cursor red because in this range you will see the color change, and 8.2 is part of it. 8.3 is very close to it. So as soon as you add a drop, just one extra drop of sodium hydroxide, the phenolphthalein is going to change color. Why is changing color? Because when it's neutralized, you end up with pH of 8.2. One additional drop is going to increase the pH over 8.2, and then the color of the phenolphthalein is going to change to the pink color. So it's going from colorless to pink color. The color change is very obvious, very good indicator when your base is sodium hydroxide. So when you are using sodium hydroxide as a standard or as a titrant in the burette, use phenolphthalein because it's going to give you a sharp change. You won't be able to use the Thymo blue because Thymo blue is not going to change color anymore after, or the color change is going to be way before the equivalence point and is not a proper choice. A proper choice of indicator is if the range for color change is very close to the pH at the equilibrium. So if the pH at the equilibrium is 8.2, the color change must include that value. You cannot have color change way before end point of the reaction or way before equivalence point for the reaction. When you perform experiment, the experiment is going to tell you which indicator to use because someone else has done the work. They found out which indicator would work best for that experiment. So if you have to choose it, you have to make sure you are looking for the pH of the color change, for the pH of the indicator, and the equivalence point for the titration. If you are using a strong base at the equivalence point, the pH is going to be higher than 7. So let me just go back to a couple more. This is a strong base. pH is at 8.72. A strong base with a strong acid, pH is at 7. So if it's a strong base, strong acid, pH would be exactly at 7 at the equivalence point. If you have a strong base but weak acid, because it's a strong base, the pH for the color change is going to be higher than 7 because you are using a strong base and a weak acid. If you are using a strong acid, and a weak base, the equivalence point will happen less than pH of 7. So for this, you cannot use phenolphthalein. For this strong acid, when you are choosing your indicator, you have to choose an indicator that the color change would be around 5, between 5.2 and 5.3. So you can't use phenolphthalein for this because if you use phenolphthalein for this one, is going to show the color change way before the actual. So it depends on the nature of your acid and base, you choose your indicator. So for that one, chlorophenol blue would be a good one because this would be between the, it would cover the 5.8. At least it's going to be between these two. You cannot use the phenolphthalein for that, or even Cursor red for that, because you had a strong acid, and for a strong acid, the equivalence point happens below pH 7. I hope that helps because you will get some questions either in the quiz or the exam based on the indicator or choice of indicator. If you have a strong acid, a strong base, you could use either one of these two. If you are using strong phenolphthalein, the color change, it would be upper range, but for methyl red, it would be at the lower pH, but still these are within the drops, like 1 drop or 2 drop difference it's not going to be a huge difference in volume. So the color change would be within 1 to 2 drop of the base you're adding. Weak acid titrated with this is a weak acid titrated with a strong base. What would be your best Because it's a strong base, I already said you have to use something that would happen, a color change would happen around pH of 8, and you could use either one of these two. Okay, I'm going to stop the recording one more time, and I will continue. No, it's like 10:43. We still have some time of the class.